guns.
Hess's law in going from a I am so sorry, I forgot. My name is Connor Trito, and I will be teaching you today. I did one section a while back, and I'm probably going to keep doing this for a while, so yay. By the way, the chemistry cat at the beginning, I drew that. Just going to point that out using the smartboard because I'm that awesome. Alright, Hess's law. In going from a particular set of reactants to a particular set of products, the change in enthalpy is the same whether the reaction takes place in one step or in a series of steps. In Hess's law, many steps or reactions are combined together, and so are their enthalpies. Important characteristics of enthalpy changes. If a reaction is reversed, the sign of delta H is also reversed. So basically turn negative. For instance, if, just pretend that's not up there until I'm done talking. Okay, for instance, let's say heat is being lost, well, as we covered last section, if a reaction is basically, if something is being absorbed, it is technically considered negative. However, if it was being produced, I'm pretty sure that'd be positive. I'm right, right? Okay. I was kind of just guessing. The magnitude of delta H is directly proportional to the quantities of reactants and products in a reaction. The coefficients in a balanced reaction are multiplied by an integer and the value of delta H. The value of delta H is multiplied by the same integer. Two forms of carbon are graphite and diamond. You know, graphite stuff that's probably in your pencil, and diamonds. I don't need to say anything about those. Using enthalpies of combustion for graphite, which is negative 394 kilojoules, and diamond is also negative 396. Calculate the delta H for the conversion of graphite to diamond. By the way, just going to point out, I suck at this, so Ms. Longmuller, you're up.
Well, thanks, Connor. Okay, so you see the equation that's listed right underneath the words. That is the equation that we want to have at the end. This is almost like elimination in algebra class, where we're going to combine the two reactions near the bottom, and until we get the top equation. And once we get that top equation, then we can add our enthalpies together and go from there. So here we go. So like I said before, we need the top equation. The graphite goes to the carbon of diamond as our final answer, and we need nothing else. But if you look at the two equations, we have more stuff. So we need to be able to eliminate the extra stuff. And in order to eliminate things, they have to be on opposite sides. If they're on the same side, they add together. So in order to do that, let's look at the first equation and look at the carbon of graphite. Carbon of graphite is on the reactant side of that equation, but it's also on the reactant side of our final equation. So that's what we want. We want the carbon of diamond on the product side, so that means we need to flip our whole entire equation so that the carbon of diamond is on the product side. So I'm going to just erase because I don't have very much room, but what I would do for you guys is draw a line through it, and then you're going to rewrite it flipped. So erasing my whole thing, you just draw a line. That means that the products are now going to be the reactants, and the reactants are now going to be the products. So that means that the CO2 is going to be on the reactant side, and that's the only product turning into a reactant. And then the two products are going to be what used to be reactants. So the carbon of diamond plus the oxygen gas. Well, if we flip the equation, then we also have to do something with the delta H, the change in enthalpy. Okay, so the rule is when you flip the equation or reverse the equation, you also flip or reverse the sign of the delta H. So if before it was negative 396, now it's going to be positive 396 kilojoules per mole. Okay, so let's look at our equation. We see that with it now flipped, the graphite is on the correct side and the diamond is on the correct side of what we need it to be to equal that final equation. Then, also, if we were adding these two together, which we're going to, so just draw a plus sign and dry line under it so you know what's different. If things are on opposite sides of the arrows, they cancel. So, looking at the first equation, we have oxygen gas on the left side of the arrow in the first equation, but in the second equation, it's on the right side of the arrow now. So that means they can be canceled. So go ahead and cross it out. It's gone. It's gone. Then, same thing goes with the CO2. On the first one, it's on the product side, and on the second one, it's on the reactant side, so it cancels out. And then there's nothing else to cancel, so we write what's left over. So that means the carbon of graphite goes to the carbon of diamond. And we have our equation that we were wanting at the top. So now that means we need to add together our changes in enthalpy, and that is our final answer. So that means we take negative 394 plus 396, and you get a positive 2 kilojoules per mole. Back to adding, subtracting sig figs, we use the number of decimal places as our sig figs, so 2 is correct. And that's how you do our first example. But I know it's kind of hard, so let's do another one, okay? Example 8. Example 8 is almost the same way. We want to calculate the changes in enthalpy for the reaction that produces sulfur dioxide. So the top equation is what we want to have at the end. And we have these two other equations to deal with to do that. So let's go ahead and do it. Alright, so with these equations, we want to have the top equation left over at the end. Okay? We're not going to just have to flip, we're going to have to do a couple things to make this work out. So the thing that I always like to do is first make sure that everything is on the correct side it's supposed to be. So starting from the left of the equation, we start out with just sulfur by itself as a reactant, and that sulfur by itself is on the reactant side. So if we look down in our two equations, the sulfur by itself is on the reactant side, so that's okay. Next we have O2 on the reactant side. Well, we have O2s in both equations, and they're both on the reactant side, so that's fine for now. And then our one product that we have is SO2, sulfur dioxide, and so that's on the product side. If we look down in the equations, the SO2, it says 2SO2, is the beginning of the second equation, and that is not on the product side. So we need to flip the equation so that SO2 is on the product side now. And when we flip the equation, we also flip the sign of the change in enthalpy. So now it's going to be 2SO3 yields, arrow, 2SO2 plus O2. And when we flip the equation, we flip the sign. So instead of negative 198.2 kilojoules, that's not going to be positive 198.2 kilojoules. Okay, so we got it flipped. Everything's on the correct side. Well, now, do we have the right coefficients in front of everything? The S is okay because it has a 1, and it needs a 1. The O's, not so much. Let's do O's last, okay? But then the SO2, down at the bottom, has a 2 in front of it, but it's supposed to only have 1. So in order for that to only have 1, we're going to multiply everything, including the delta H, by 1/2, or we're going to divide by 2. Two ways to think about it. Either divide by 2 for everything, or multiply by 1/2. So that means all of the coefficients change, as well as the change in enthalpy. Alright, so that means that now there's going to be 1 SO3. You don't really have to put the 1 if you don't want to. There will be 1 SO2. And there will be 1/2 O2 in the bottom equation. And so then we need to take 198.2 divided by 2. And you get 99.1 when you divide by 2. Now we can go ahead and cancel. So if we're adding these two lines together, we first want to cancel out things that cancel. So the SO3s, there's one of them on either side, so those will cancel out. The S is on the correct side, and the SO2 is on the correct side. So we're good there, but now we've got to deal with these oxygens. Okay, so we have 3/2 oxygen on the reactant side of the first equation, and 1/2 oxygen on the product side of the other equation. Remember when I said if they're on opposite sides, they cancel out? Well, in this case, if they don't just cancel completely to 0, the one side with more left over will be the side where the O stays. So we subtract. So we're going to take 3/2 minus 1/2, and you get a 2/2 or 1 whole one. So then that would just be SO2 left over. So now that we have our equation we want, we can go ahead and add our two changes in enthalpy together. So if you take negative 395.2 plus 99.1, you get negative 269.1 kilojoules. Again, sig-figs for adding and subtracting. The number of decimal places needs to stay the same. So if we have one decimal place, we keep the whole number that we have. So that is our final answer.
Shout out to Taylor Sell, because no one shouts him out, I guess. And shout out to Clay, my main man, sitting in the room currently, looking into his laptop, smiling kind of. Yeah, that's about it. Hope you guys had a fun time learning. I did. Be on the cell, I could really use a muffin right now.